SEC approved doing security consulting. They're a pretty cool place. I'm just briefly mentioning them because most of the work done to prepare this talk was on non-billable time there, so they paid for it, kind of. This is just a quick outline of what I'm going to talk about. And first, I'll talk about Line, which is a messaging application, just like WhatsApp or WeChat or Facebook Messenger, or any of those other countless messaging applications. It got created back in Japan in the wake of the earthquake in 2011, and because in large part the telecommunications infrastructure was pretty bad at the time in the wake of the disaster, and so it was often the case that people would have cellular data, or maybe Wi-Fi, but not the ability to make actual calls. So this application supports calls over data, and that was basically the entire thing that caused it to get popular in Japan. And after becoming popular in Japan, it eventually spread to Taiwan, India, Spain, and some other countries. And it's really useful to me because I have a bunch of Taiwanese friends who it's most convenient to talk to on it. And yeah. But last fall, they added end-to-end encryption. Yay. And if you're not very familiar with end-to-end encryption, then you might be wondering, weren't they already encrypting their messages? And yes, kind of. Everyone encrypts messages between the sender of a message and the server, and then between the server and the recipient when they download the message from the server. And Line was doing that, of course. But then Line can still see your messages, and so can a government. Like if the Japanese police are investigating something and they ask Line for data, then they may be legally required to give the police your message contents. Or someone who hacks into Line servers can read your messages. And that kind of sucks. So what if instead of just encrypting between server and client, what if we encrypted to some particular key that only you and the person that you're sending the message to actually has? And then the effect of that would be that Line can't read your messages. Governments can still compel them to cough up the ciphertext to your messages, but they're not going to be able to decrypt them because they don't have the key, and no one can break into their servers and read your messages by just breaking into their servers. And nowadays, all of the messaging platforms are adding this sort of feature. Textmessage or Signal was originally is only for end-to-end encrypted messaging, but a lot of other messengers are adding this as an usually optional feature, like WhatsApp, Facebook with its secret chats, Google's Allo with its incognito chats, iMessage, a bunch of others, some of which are less well implemented than others, and now finally Line. And not everyone's doing it the same way. A bunch of the more recent ones are using the same encryption scheme that Signal pioneered. Nowadays it's called Signal Protocol. It used to be called Axolotl, but a lot of messaging platforms have their own protocol for this, and in particular, Line does. They call their end-to-end encryption feature letter sealing, and they have a blog post about it, which has a little information. It tells us that they use elliptic curve Diffie-Hellman for key agreement. It tells us that they use the advanced encryption standard, with a 256-bit key in CBC mode for encryption. And it vaguely describes a hash and encrypt function of the plaintext as what they're using for their message authentication code to make sure that message ciphertext aren't modified in transit or by line, or are actually coming as they were sent by the person sending the message. But it's missing a lot of details. For example, how did they generate the ID for the encryption? This can be a big deal because if you, for example, just have a static ID, then if someone sends the same message multiple times on the same key, then you can see that they sent the same message. And there are various other issues depending on how they're generating and communicating the initialization vector for CBC mode. And there's also the question of how do they actually generate the encryption key itself? Is it just the shared secret that they computed with elliptic Diffie-Hellman, or did they do something else to it? Then there's also the question of what is this hash and encrypt function that they're using for their Mac? And what is it being keyed with? Then there's also the question of what elliptic curve are they doing ECDH on, and how are they actually like formatting the messages when they're transmitting them? Because that will also affect how you could, the difficulty of exploiting other vulnerabilities, and what actually gets encrypted. And well, if they're not going to tell us all these details, then we just have to reverse their apps and find out. It can't be that hard, right? It actually was kind of hard, but that's just because I am new to reversing and stuck at it. But it's still not very hard. It's just a little hard. And one thing making it a lot easier is that they have tons of clients. They have one for Macs, for Windows. They have one. They have a Chrome app. They have apps for every major mobile platform, including ones that I didn't know existed or had, and ones that I didn't know still had people making things for them. And the thing is, if these apps, if someone on an iPhone can message someone on an Android phone, then clearly the communications are going to have to be intercompatible. And sure, it's not impossible that they could have a different scheme for doing the encryption for each one, and it just happens that each other application can handle decrypting all of them, but no one's going to actually do that. So probably they're using the same encryption protocol to implement this letter sealing feature for communicating between all of the different platforms, which means we really only have to look at one of them, or, well, to find out how the protocol itself works. Looking at others is still useful because then we can see if there are flaws in how they're implementing that protocol, as well as potentially flaws in the design of the protocol. But first I actually decided to look at the Mac app, their desktop Mac application, but it was an enormous pain because it was written in C++, and I didn't want to have to dig through a gigantic binary that frequently crashed Hopper to figure it out. So instead, I decided I'd start out by looking at the Chrome application, because as a Chrome app, it's just going to be HTML and JavaScript and CSS. And that's, sure, it's going to be obfuscated, but it's not going to be as distant from the source as a compiled binary. So I looked at that, at the Chrome app first. And it's straightforward to actually get the Chrome app, and then since I'm going to be wanting to look at the source, obviously you need to look at the, you have to find where the Chrome app's actually getting saved, which, if you're not familiar with Chrome apps, is going to be in within your Chrome profile directory under extensions, under some not clearly meaningful ID, which you can get by looking at the Chrome extensions page if you have developer mode enabled, and then under a version for it. But my first thought was, okay, it's going to be talking to there's probably over HTTP, so let's just send Chrome through burp and look at the traffic. But as you can see, this is the body of a request that got sent when I tried to send an end-encrypted message. It also looks basically the same as if I sent a non-end encrypted message. It's not very helpful, so we should. We still know where we can still tell where it's sending that to from the proxy, because that's not in some bizarre binary format. And so I decided to look at the JavaScript and try to find where it was referencing the paths and hosts I was doing. But before I dig into that, I'm going to talk a little about how the application's source code is actually structured. And there's a main.js file, which is just a tiny file that creates a new window holding a particular HTML file, their index.html file. And that index.html is basically just sort of the basic skeleton stub of the AI, and has templates that will be used to populate the rest of the UI, and two script tags for these not very informatively named files. Ukao, if we want to call it that, or cookme.js. And the first of those files also creates a bunch of web workers running a bunch of other scripts that also have meaningless names, which in a few cases go on to load some more scripts, but pretty straightforward still. And file names are not helpful at all, and in fact they appear to be random, since there have been a few different versions of the line Chrome app since I started looking at it, and in every version they're roughly the same files, but they have completely different names and similarly completely meaningless. And so the file names aren't going to be helpful, but some of the files use the AMD API, which is a module definition API for JavaScript. And for those, we'll at least have an idea of the module structure of the application, which parts of the application depend on which others. And in a few cases, they even have names that are meaningful and haven't been obfuscated in any way. That's pretty useful. But the source is still obfuscated all throughout. First, it's minified. It's clearly minified. There's a screenshot there, and it's just all structured. And so I use Ekoparty.js to beautify that. And here's the beginning of the file now. And that's a lot easier to read than this mess, but it's still a little weird. What is this A subscript? Who knows what that is? My LaTeX template can't even handle that anymore. Like a bunch of the letters are missing. So here's a screenshot from my editor, which is even weirder looking, but it's there. But, you know, it's really just some harmless name mingling. And fortunately in this file, in the file beginning with UC, there's sort of a key. There's this big variable declaration statement that has these files, and they has these mangled names and maps them to string constants. like chat location, Google Map URI, or as it turned out to be for this meaningless one from the slide before, length. So it's just getting the length of an array. And in this one file, there are 35,000 bytes of that key. The good thing is it's really, really easy to deal with mingled names that are that weird because they're not going to accidentally appear. You can just do a string replace on everything without having to use something that's a little more aware of JavaScript syntax or anything like that, or having a risk of mistaking one thing for another. But some of the files do not have a key like that, so we're going to have to actually look at what the code is doing and figure out what it's supposed to do without getting to just rely on names. Now, earlier, I said that I was looking for where the code referenced the endpoints that it was sending requests to when I sent a message, and that endpoint is this https://gf.line.navier.jp/s3. So I went to look for that one, and that string as a whole doesn't appear at all in the source, but I figure they probably broke it up into the path and the host. So fortunately, the host name and the path name do appear in pieces of code that set keys on what looks like some sort of config object. One of them sets this server info thrift host to the host name and server info auth URI to S3. So we want code that's using both of them. And in this other JavaScript file, yubsp, we find some code that builds an AJAX request to that URL using those methods. And it gets used with T-binary protocol and talk service client. So I went digging for those. And T-binary protocol, you can easily find out by Googling, is just one of the serialization protocols for the Thrift remote procedure call system. And cool. I don't really want to be digging into a bunch of Thrift stuff because that's a bit of a pain. So I started looking at the talk service client. And that's defined in yet another file beginning with Y. And it had a bunch of groups of 3 methods together that looked a lot like this. There would be one method that called the second method, and if there was a callback supplied in the third argument, it would also call the third method. And then then in the second method, it would do various stuff with the output field of this object, and then might eventually call the callback. And then in the third method, it did various stuff with the input field of this. And then at the end, if it hasn't already returned, then it will end up throwing an error that looks like something like this. Get buddy detail failed, unknown result. Or it might be register E2E public key, failed unknown result. Or send message, or all sorts of other things. But the names in those strings are meaningful, fortunately. So it's really easy to figure out, okay, this first method, this trio of methods must be something that will do a remote procedure call to the, for example, get buddy detail method on the server. I'm not sure what's going on. Apologies for the blinking. Technical issues here, it seems. No. There we go. So I started digging into the send message one, and I'm not expecting to be able to read that snippet of source code, but it traces back into the send E2E message. And send E2E message eventually finds itself calling another method called encrypt E2E text message, which sounds like exactly what we want to find out about. And that method is here. And I know it's small, it's hard to read right now. It calls a bunch of mangled functions. And fortunately, it will turn out that a lot of those are really easy to read. And since it's such an important function to their encryption protocol, I'll go over it in more detail and use an example of like the process that I followed to figure out each of the calls in application. And it's really hard to read with everything crunched in on a few lines like that and such. So and without any if or other explicit control structures, instead relying on the and logical operator. But so first I reorganized it a little by separating out those comma operators into separate statements, which again makes it really gigantic. But some of those are pretty dumb. Like they have 5 calls to push, which on the same array right after one another. That's kind of pointless. They can be put together. That makes it a little easier to read. And then this is a matter of taste, but it's really annoying to me to read 0 equals f length and d call d with null. So I turned those into f statements. But now that it's fairly easy to see where the things are being called and with what, we can dig into the actual name angle function to figure out what they're actually doing. And so I'll start out with this first one, which turned out to be the only function with that name in the entire file, or indeed in the entire source code. So it was really easy to track down. And it's also really easy to read. It just gets 8 bytes that are cryptographically random from the browser's cryptographic random number generator. So I decided to call it 8 random bytes, whatever. And so 1 function down, only a bunch more to go. The second one gets called with the key data field of one of the arguments, and also those 8 random bytes that we just generated. And it's a big function. You might not be able to read that very clearly, I don't know. But there are a few string literals and non-obfuscated function calls that make it actually pretty clear what it's doing, and it's pretty clearly taking SHA-256 hashes of things and sticking them in the AST and IV. And if we figure out what the functions calling and such are, then we can figure out that, oh, it looks like this. And we can see where the different things that's taking SHA-256 of are, and where they're getting put. And it turns out that the AST looks like the SHA-256 of concatenating the the key data that gets passed in with the random bytes that get passed in, and then the string key. And then they just take the SHA-256 of that, and that's apparently their AES key. Okay? And then they do the same thing with IV instead of key for the IV, but since initialization vectors in ASCBC are going to be 16 bytes instead of the 32 bytes that SHA-256 produces, they call another function that I've called XOR first and second halves on the result, because it basically divides the byte array that's passed in half and takes the XOR of those two halves. So we now can figure out, we now see that second function was just generating the AS key and IV from their secret key and assault. Now, they do a bunch of stuff to set some metadata related to their end-to-end encryption on what looks like it might be the message, and they do some other various formatting on the text property of the message. Now, before finally passing that into a bunch more name-angled functions. And I'll start from the outermost one on this line, which looks like this. Conveniently, these methods didn't even get name-angled, so we didn't really have to dig into trying to guess what they were based on magic constants and things like that. But it's pretty clear that this one is just doing ASCBC encryption. And there are a bunch of mangled functions, but all that they do is convert between different ways of representing strings, like convert a hex string to a byte array, or to a base 64 encoded string, or even just an actual binary string. But this function that gets called with the result of, though, is also ridiculously simple, and it just wraps the message in a JSON object. The processing that they do before it looks like it does suitably prevent it from ending up as not a valid JSON object. So that's nice, though not critically important. So this H ends up really being the message ciphertext, and it ends up getting passed into these later functions on the next line. And I'm once again going to start from the outermost one on it, which turns out to just base 64 decode string. So that's straightforward. The next one is a little more interesting. It calls another function, which then does AS ECB encryption without any sort of padding, which, okay, they don't need padding because they know that what they're passing in is the result of this next function, which is much like the process followed to generate the IV. They're taking the SHA-256 hash of something and then XORing the first and second halves of that. In this case, what they're doing that with is the ciphertext, since the ciphertext is what gets passed in. Which means that which apparently they are signature, because they talk about a hash and encrypt function, and that's precisely what they're doing. They're taking the SHA-256 hash, they're compressing it a little by XORing it against itself, and then they're encrypting that. Now, there's only one more name-angle function, and it's annoying to read because of all the commas, but it's just the big ending encoding of an integer. And so we end up with this much clearer version of encrypted text message, which generates a salt, then if there's no key data, calls the callback with null. Otherwise, well, either way, it continues on to generate an AS key and a salt, and then does some stuff with the metadata, and then some processing on the text prior to finally encrypting it in AS and CBC mode with the key from above. And then we have our signature being computed, as we discussed. And then we stuff them all together. We stuff the salt, the ciphertext, and the signature together, in addition to the big Indian encodings as byte arrays of the sender key ID and the receiver key ID. And then that gets stored in the chunks field on the message, and then passed on to the callback. There's a pretty similar function for decryption. I've gone ahead and included the sort of decoded version of it. So the ProMap was pretty simple to look at. The iOS app was the other one that I looked at the most, and it's not quite as trivial. It's, at least for me, a lot harder to read disassembled, even Objective-C code than it is to read JavaScript. But at least Objective-C makes things a little bit easier, because the message calls that are made by Objective-C on Objective-C objects, they're handled at they're actually stored as strings, the selectors are. And it's a little more efficient, I think, than actually looking up a string in a hash table every time, but it's still storing those message names. So we know what their function calls are, unless they obfuscate them, which it's certainly possible to do in a lot of cases. If you're using messages that are part of particular protocols that are necessary for interoperating with the built-in APIs and such, you're not going to be able to obfuscate them, but for a lot of things you can. So that's great and all. But line did not even do what they could. So that makes it a lot easier. The unfortunate thing is that it's a gigantic pain to talk about them because their methods are still very big. Sorry. This is a rotate control flow graph of the disassembly that I generated with Hopper, and it's gigantic. You don't want me to walk you through every bit of that. And realistically, I'm far from an expert on binary reverse engineering. You should probably read a book or talk to someone who's more familiar with about that. And it's also the case that it ended up being basically the same as the ProMap. This gets cut off a little because Objective-C is very verbose and extends far over the column, but it looks a lot like it. Now that I've gone over the implementation and the process of works, I can actually describe the protocol itself. So the key exchange works using ECDH with curve 25519, DGB's elliptic curve, to generate a shared secret from the public key of your recipient and your private key. And then you SHA-256 that with the salt plus the key. You get your AS key. Then to get the IV, you do the same thing with IV instead of key. And then you XOR the first half of that with the second half, and you get your IV. So then you serialize the message object to JSON and use that message key and IV to ASCBC encrypted, and it's that simple. to actually authenticate, to generate the macro message, you SHA-256 that ciphertext and do the same storing first half against the second half. Then you AES encrypt that with the messages encryption key and get the MAC. Then you transmit that as we discussed before. And finally, I'll talk to you about of one I found in the Chrome app, which signature checking. This is what the signature check in the Chrome app looks like. If 0 not equals signature.sig bytes. That doesn't sound right. Indeed, signature checking on iOS actually does something. It uses this verify signature message, which actually does things. But as we saw on Chrome, it doesn't do anything. And so you run into the issue of like potential message forgery. For example, like a CBC bit flipping attack, where if you modify a particular bit in one block of the ciphertext, you can see that will scramble the decrypted plaintext of that block, but the next block, the corresponding bit will be flipped. So that sort of attack might be a little tricky to get while still preserving the format of the expected format of the message, but particularly on longer messages, it can be quite possible. The good news is they fixed it last Monday. And Chrome apps, they update automatically, so presumably anyone in the world who's using their Chrome app no longer has this issue. But there are a few design weaknesses in my view, which is that only the message text is encrypted. For example, no time or sequence number or anything for the message. Someone could incorrectly repeat the message or stuff like that, or claim that it came at a different time than it actually was. And there's no notifications if the key for the person you're talking to changes. So even if you verify the key at one point, you can't, unless you go and check again, you won't know that they still have the same key that you verified. And the Mac is okay, but I for one would feel a lot safer if they were using some sort of HMAC, but yeah. Are there any questions? Just because I use it personally, and I fear it seemed like no one else was looking at it. Anyone else? I can't see anything. I think I'm done.
¿Hay alguna pregunta para hacer? Si no, Tyler va a estar en el salón de aquí al lado y ahí se pueden juntar con él y hacerle cualquier tipo de pregunta. Bueno, muchísimas gracias.
Gracias.